Please confirm. Question. Okay. Yeah, students. Yeah, very good. Give the answer. I'm waiting for your answer. All right. So first thing, in the given question, signed data given, right? Consider the following signed data. User point of view, you know it is a signed data, or it is unsigned data, or it is a decimal data, and so on. So user point of view, data may be in different formats, but computer point of view, data is always present in the binary format. So here, binary data given, okay? So we are going to apply the addition operation, perform the addition operation. Addition operation takes place on the given data. Later, we need to find out the status of carry flag, overflow flag, zero flag, and sign flags. Okay, we need to find out the status of the flags after the data processing. Data given, operation given. Now perform the addition operation and report the answer. Okay, right. So given data is 1101 0001. Next 1101 0010. Operation addition. Operation takes place between the data is addition operation. Now adding them 1100 0 carry 1, right? 0 carry 1, 1 carry 1. This is the addition. After the data processing, all the conditional flags are evaluated. As far as our subject analysis is concerned, 8086 CPU supports 6 conditional flags. So all the 6 conditional flags are evaluated. But question point of view, we need to answer only the carry flag, overflow flag, zero flag, and sign flag. Right. First carry flag. Condition of the carry is there an extra bit out of MSB? See this? Out of MSB, extra bit is present or not? Present. So condition true. Flag is set. So carry equal to 1. So carry present, character representation is C. Carry set means character representation is C. Alright. Next overflow. Overflow flag condition is there is a carry into the MSB and no carry out of the MSB or vice versa. This is the condition of a overflow flag. So after the data processing, verify the condition. When condition is true, flag is set, otherwise flag is reset. Okay. Now see this. Here there is a carry into the MSB and also there is a carry out of the MSB. Carry into MSB, carry out of MSB. So condition false. Therefore flag is reset. So overflow flag is 0, reset. Reset character representation is NV, no overflow. Next, 0 flag. 0 flag condition is the ALU output accumulator value 0? See this. This is the accumulator value. Is the accumulator value 0? No. So condition false. Therefore, 0 flag is reset. Reset means NZ, non-zero. Non-zero. Okay. Right. Sign. Sign flag condition is the MSB bit of ALU output. That means accumulator contain 1. See this? MSB bit of ALU output accumulator. This one. Contain 1? Yes. So condition true, flag is set. Set means character representation is NG. NG stands for negative logic. Okay, students? So after the data processing, carry flag is set, overflow flag is reset, 0 flag is reset, and sign flag is set. Okay, so binary representation is 1001. Character representation is C, NV, NZ, NG. Carry, no overflow, non-zero, negative logic. Okay, students? So based on this analysis, go to the given options and select the right answer. Okay, so right answer selection is here. A is right answer, 111001. Then C is right answer. Carry, no overflow, non-zero, negative logic. So A and C is the answer. Okay, students? Yeah. This is the analysis. A and C. So many students are given the right answer. Yes. All the students, maximum students given the right answer. And few students are given only A option. But here C option is also correct. C means carry, NV means no overflow, NZ means non-zero, NG means negative logic. Okay, students? All right. Next question I am going to display on the screen. All of you see the question. Try to solve it. Question is on the screen. Do it fast. Tulsiram, correct answer. Yeah. See students, here question is, consider the following hypothetical format used to represent the data. So format given and also data given. Format given, data given. Okay. So sign, biased exponent, Mantissa. This is designed with a excess bias. So format is designed with a excess bias. All right. So this is the data, minus 17.25 into 2 to the power of minus 12. Okay. So this data we are going to store into the memory using the given format. Okay. By using this format, we are going to store this data into the memory. All right. Then what is the hexadecimal equivalent when it is stored in the memory using the above format? Okay. When the data is stored in the memory using the above format, what is its hexadecimal equivalent? Right. So this is the data storage process. So you know already the process of data storage into the memory using floating point format. Okay. Apply the same logic. Store the data, later group 4 bits and give the hexadecimal equivalent. Students, solve it. I am waiting for your answer. Mansi, answer please. Tulsiram. Okay. Yeah. Biplab Roy given the answer, that is C. Yeah, Devanshu given the answer. Yeah, students already started the answers. Okay, so let me analyze the question quickly. So here format mentioned, excess bias format, data given. So first to take the given data. Given data is minus 17.25 into 2 to the power of minus 12. Okay, so this data is a binary data because base of the data is 2. It is binary data, but some part of the data is present in the decimal format. So convert that decimal formatted data into the binary. So that is minus 17, 10001.2501 into 2 to the power of minus 12. This is the binary equivalent of the given data. Now apply the normalization. That means before storing the data into the memory, we need to verify whether data is present in the normal format or not. Normalized format is 1.BBB. This is the structure. Before decimal point, there should be only one digit, that should be 1. Okay, so when we verify our data before decimal point, total 5 digits are there. Okay, we don't want 5, we want only 1. Therefore, this data will be aligned to right direction 4 times. Aligned to right 4 times. Okay, so when the data is aligned to right 4 times, exponent is incremented by 4. That is minus 1.0000101 into 2 to the power of minus 12 plus 4. Exponent incremented, right? So this is equal to minus 1.0000101 into 2 to the power of minus 8. Okay, students? Yeah, this is the normalized data. This normalized data we are going to store in the memory using the format. So format given is Sine, BE and Mantissa. This is 1 bit, Sine is 1 bit and BE 10 bit, Mantissa 9 bit. 10 bit, 9 bit. So this is excess bias. Right. First, sign of the data is negative. Negative sign is represented with 1. Then second, BE equal to AE plus bias. BE equal to AE plus bias. Okay. What is the AE value? AE value is minus 8. So 8, 0, 0, 0, 0. 10 bit code we want. Right? 2's complement of 8 is minus 8. 1's complement plus 1. This is minus 8. Okay, students? 2's complement of data is negative of a data. Right. Now, AE actual exponent is 1111 111 0 0 0. Then bias is excess bias. It is not a normal bias. This is an excess bias. So excess bias means bias value equal to 2 to the power of n by 2. This is 2 power 10 by 2. That is 512. Right? So bias is this. Now adding it 0 0 0 1 1 1 1 1 1 0 1. This is the BE. Then third one is Mantissa. Mantissa of the data is 1.000101. Correct? Now store this into the format. Format given is sign negative, BE 0 1 1 1 1 1 1 0 0 0, 10 bit. Okay. Next, Mantissa. Mantissa means only fraction, 0 0 0 1 0 1, and remaining all are zeros. Yes, this is sign, this is BE, and this is M. Now group 4 bits and report the hexadecimal equivalent. Group 4 bits and give the hexadecimal equivalent. What is the answer? One zero one one. That is D. F 0 2 8. This is the answer. All the students are given the answer as CCC. Okay, so if you look at the question, students, this is the question. So here in the C option, this is not F, this is D. Yeah. Okay, format given, data given. We need to store this data into the memory using this format. Okay, so when we store that data, first to take the raw data, convert that into binary, check the normalization, so this is not in the normal format. Align the data to right direction 4 times. When it is aligned to right 4 times, exponent is incremented by 4. So this is your data, normalized data. This normalized data stored into the memory using the format. This is the format, excess bias format. Okay, so sign is negative. Negative means binary bit is 1. Biased exponent equal to actual exponent plus bias. Okay, so actual exponent is -8. 2's complement of the data is negative of the data. So here 10 bit space is allocated. So 8 is represented with 10 bits. 8 is represented with 10 bits. 2's complement of 8 is negative of 8. That means -8. So this is the actual exponent. So actual exponent plus bias, that is equal to biased exponent. Okay, so this is the actual exponent. Bias is excess bias. Excess bias means 2 power 10 by 2. Okay, now adding this is the B. After that Mantissa. Mantissa value is 1.00101. That is the normalized Mantissa. So we take in normalized value 1.m. Okay, so sign is 1, BE value substituted here. Mantissa, only fraction part is substituted, and a zeros padding is takes place at LSB because of the fraction. Later 4 bits are grouped, value become DF028. This is the hexadecimal equivalent when the data is stored in the memory using the given floating point format. Okay, students? Alright. So if you see the options, in the options actually C option is matching here. C, DF028. Okay, you need to verify this. DF028. This is the answer. Okay, right. So next question. See this question. All of you see the question which is on the screen. Try to solve the question. Because in the data representation topic, there are two formats available, fixed point format and floating point format. Fixed point format point of view, we are going to concentrate on the unsigned numbers and signed numbers. Okay, floating point data point of view, we are going to concentrate on the single precision floating point and double precision floating point. Okay, so floating point data point of view, there are only two cases present: how to store the data, how to retrieve the data. Okay, storing concept already given in the previous question. This is the retrieving concept. Okay, all of you see the question and solve the question. I'm waiting for your answer. अरे या स्टूडेंट्स, अरे प्रीवियस क्वेश्चन में या this is not D, this is B, right? B, BF028. Yeah, thank you. BF028, correct. Previous question, BF028, that is right. Okay, when we are grouping 4 for binary bits into hexadecimal, 1011, that is B, not D. Okay, BF028, that is right answer. Okay, thank you. Mansi, thank you so much. Yeah, BF028, that is right. Thank you, Mansi. Pallav Jain, thank you. Shobit, thank you. BF028, correct. Then what about this answer? Shakir Ali given the answer B. Shobit given answer B. Dark shadow also given answer as B. Then what is the right answer? Okay, now see this question. Consider the following memory data present in the memory using the following format. This is the format given. 1 bit is allocated for the sign, 9 bits are allocated for BE, and 14 bits are allocated for M. This is the memory data, means data which is stored in the memory already given. 0x, 0x stands for hexadecimal. So hexadecimal data given in the question, that is stored in the memory using the floating point format. Okay, right. What is its decimal equivalent? We need to find out the decimal value of the hexadecimal equivalent. Okay, students? Yeah. So reading process already known to us. That is, first to take the memory data. Memory data, that is 0x40F800. Okay, this is hexadecimal. 0x stands for hexa. So convert this into binary. 4 0 1 0 0 4 0 0 0 0 0 F 1 1 1 1 8 1 0 0 0 and remaining zeros. This is the binary, right? Binary code with respect to the given hexadecimal code. Now this binary code is placed into the format. In this format, 1 bit is allocated for the sign. This is sign. And next 9 bits. 9 bits are allocated for the BE. And remaining 14 bits are allocated for the Mantissa. Okay, Right. So according to the given data, directly we can place the binary code into the value format. That is -1 to the power of s into 1.m into 2 to the power of be minus bias. This is the structure to report the value. So -1 to the power of s, in place of s 0 is there. 1.m, in place of m 111,000, remaining all are zeros present, into 2 to the power of be. Okay, in place of be what is present? See this? This is 1, this is 2, 4, 8, 16, 32, 64, 128, 256. Okay, 256 plus 3, that is 259 minus bias. Bias depends on the format. In this question, format given simply BE mentioned, nothing given about the bias representation. So that default bias is normal bias. Normal bias is maximum possible positive exponent is the bias. So here bias equal to plus 2 to the power of n minus 1 minus 1. That is plus 2 to the power of n value 9 minus 1 minus 1. That is plus 255. Okay students, 2 to the power of n minus 1 minus 1, that is maximum possible positive exponent. That is the bias, normal bias, right? So n is number of bits in the BE, 2 to the power of 9 minus 1 minus 1, that is the 255, right? This is plus 255. So minus 1 to the power of 0 plus 1.111000 and so on into 2 to the power of plus 4, right? So I want to give the decimal value. To give the decimal value, make this exponent 0. Make this exponent 0. To make the exponent 0, align this data to, align the data to left direction 4 times. Align to left 4 times. So when the data is aligned to left 4 times, exponent is decremented by 4. So plus 4 minus 4. So exponent becomes 0. Therefore take the positional weights and report the answer. So here data become plus 1110, 4 times left element, 0.000 and so on into 2 to the power of plus 4 minus 4. This is cancel. Now report the decimal value. This is 1, 2, 4, 8, 16. This is equal to how much? Plus 30. Answer is plus 30. So decimal equivalent of the given hexadecimal code is plus 30. Now move to the question and select the correct answer. Correct? So answer is plus 30. B is the right answer. B is the right answer. Okay students? Hope you understand the way of retrieving the data. In the previous question you know how to store the data. Okay, so floating point formats point of view, we should practice the questions related to storing and reading. Okay, how to store the data into memory and how to read the data from the memory. Okay, so answer is B. Let me see how many of you are given the answers. Yeah, Srijal given answer as plus 30. Karthik, Mansi, Shobit. Yeah, all the students given the same answer. Okay students, all right. So answer is B. Very good. So go to the next question. Right. Students, next question is on the screen. All of you read the question and try to solve it. Waiting for your answer. Do it fast. what the question states. Amrit, you are asking the question stating that, sir, is the bias is not 256? Previous question, Amrit, you are asking that, sir, bias is 256. No, because in this question, they given the format with a normal bias. Normal bias is maximum possible positive exponent. Okay, so here plus 2 power n minus 1 minus 1. This is the maximum possible positive exponent. That is the bias. Okay, in the previous question, they given the excess bias. Excess bias means center of the exponent range. Center of the exponent range. So normal bias is plus 2 power n minus 1 minus 1. Excess bias is 2 power n divided by 2. Okay, already you know the concept of normal bias and excess bias. So this is mentioned in the question itself. If nothing is mentioned explicitly, by default take the normal bias. Okay, Amrit? All right. Yeah, this is our current question. Okay, students, see the question. Consider a system which supports 32-bit format. This is a system which supports 32-bit format. You know, floating point formats are IEEE formats. Okay, only two formats available, 32-bit and 64-bit, single precision and double precision. So here question clearly states that system supports 32-bit format. Now we are going to take the 1-bit sign, 8 bits BE, 23-bit Mantissa. That is the 32-bit layout. You should remember the layout of the 32-bit format, because only two formats given by IEEE standardization, right? Single precision and double precision. Okay, 32-bit and 64-bit. All right. This is addition operation is performed on the following data. So here operation is addition. Addition operation takes place on the following data. So two data elements given, we need to perform the addition operation. Okay, after the addition operation, we need to report the result in hexadecimal format. Okay, take the data, apply the addition, and store the result into memory using the format and report the answer in the hexadecimal format. Okay, students. So you know the procedure of the addition. When we are taking the addition operation, first thing is consider two numbers, given numbers. First number treated as x, second number treated as y. So take two numbers. All right. And second point is we need to compare the exponents of two numbers. Two numbers exponents we need to compare. Okay, suppose two exponents are same. You know? So what is the meaning? I am going to take the difference between the exponents. Okay, second number exponent is subtracted from the first number. Okay, so if that difference is 0, that means both the exponents are equal. Directly we can take the exponent as a common, add the Mantissas, normalize the result, store the result into memory. Very good. Suppose exponents are not same, then take the smaller exponent Mantissa, align to right direction up to the difference. That means we need to equalize the exponents. After equalize the exponents, take the exponent as a common, add the Mantissas. Okay, normalize the result, store the result into the memory. This is the procedure. Okay, students? Right. Now apply the same procedure on the given numbers. Okay, first take two numbers. Step 1. Procedure is step 1. Take two numbers. Okay, x equal to plus 1.1001 into 2 to the power of plus 8. Then y equal to plus 1.0101 into 2 to the power of plus 4. Two numbers I taken. Right. Next, second step. What is that? Compare the exponents. I compared two exponents, 8 and 4. Both are not same. Now take the difference. Difference between two exponents, 8 minus 4. This is equal to 4. 8 minus 4. Exponents difference. Exponents difference I taken. exponents difference. Okay, so that is the 4. So take the smaller exponent Mantissa, align to right direction 4 times. Smaller exponent Mantissa is y. So take y and align to right direction 4 times to equalize the exponents. Okay, when it is aligned to right direction, y is equal to, what is the y value now? Plus 0.00010101 into 2 to the power of plus 4, exponent incremented by 4 times, because right alignment 4 times, exponent is incremented by 4. Now data is plus 0.00010101 into 2 to the power of plus 8. This is the data. So after second step, we equalize the exponents. So x exponent, y exponent both are same. So take the exponents common, add the Mantissas. Step 3. X Mantissa plus 1.1001, y Mantissa plus 0.0001, 0101, okay, add them 101000101.1. So this is the exponents addition, x plus y, sorry, Mantissa addition. X Mantissa, y Mantissa, both the Mantissas are added. Okay students, then step 4. What is the final result? Final result is plus 1.10100101 into 2 to the power of plus 8. Because exponent is taken as a common, we are adding the Mantissas. Now this is the final value. Final value is already present in the normal format, 1.BBB. Is it in the 1.BBB? Yes. When it is in normal format, directly we can store the data into the memory using the floating point format. Okay. So what is the floating point format? 32-bit format. Step 5, store the result into the memory using the format. 32-bit format means 1 bit is allocated for the sign, 8 bits are allocated for the BE, 23 bits are allocated for the Mantissa. This is the standard format given by IEEE with respect to 32-bit format. Okay, right. First, sign. Sign of the data is positive. Positive sign is 0. Right. Second one, BE equal to AE plus bias. All right. Now what is the bias? Bias is normal bias or excess bias. By default, IEEE bias is normal. Normal bias means plus 2 power n minus 1 minus 1. So n value is how much? 8 minus 1 minus 1. That is plus 127. This is the bias. Bias of the IEEE 32-bit format is plus 127. Normal bias. Right? Now actual exponent plus 8. So 0, 0, 0, 0, 1, 0, 0, 0. This is the actual exponent. Now bias. Bias of the format is plus 127. 0, 1, 1, 1, 1, 1, 1, 1. Adding them. Right? Yeah. This is the biased exponent. Actual exponent plus bias, that is equal to biased exponent. Alright. Next, third one, Mantissa. Mantissa is already present in the normal format. What is the normal Mantissa? 1.1001000101. This is the normalized Mantissa. Alright. Now store this information into the 32-bit format. Sign. Sign is positive 0. BE 1000011. Next Mantissa. Mantissa means only fraction part is stored. No need to store the valid bit. Okay. So fraction part 101000101. and remaining all are zeros. Zeros padding takes place at LSB. Zeros padding takes place at LSB because of Mantissa is a fraction. Okay. After that, group 4 bits to report the hexadecimal. Okay. 4 bits. Like this. 4 bits grouped into one hexadecimal. So 0100 that is 4, 0011 that is 3, 1101. Now this is D. Okay. Earlier there was a confusion. Na? Okay. In the second question, 1011 that was B. 1101 this is D. Okay, students. Right. 0010 this is 2. 1000 this is 8. And remaining all are zeros. Okay. 1, 2, 3, 4, 5, 6, 7, 8. 8 into 4 that is 32. Okay, students. So hexadecimal equivalent of the result after performing the addition operation is 43D28000. This is the answer. How many of yours answer is matched? You please verify. Base H. This is the answer. Okay, students. Yeah. 43D28000 is the answer. Yeah. Pallav Jain. Very good. Pallav Jain given the right answer. Tulsi Ram also given right answer. Srijal Patel given right answer. Shakir Ali given right answer. Thank you so much, my dear students. That means you are in the perfect track. Okay. When question is present, automatically you know how to solve the question. That's what you given the right answer. Okay. Very nice. Okay. You just verify the procedure once again. First thing, take in the given numbers x and y. 2 numbers I taken. Right. Later I equalize the exponents. First take in the difference between two exponents. When the difference is 0, that indicates both the exponents are same. When the difference is non-zero, that indicates exponents are not same. Then take the smaller exponent Mantissa, align to right direction up to the difference. Here the difference is, exponent's difference is 4. Okay, smaller exponent data is y. So this y number is aligned to right direction up to 4 times. Okay, so that exponent is equalized. Take the exponent common. Okay, add the Mantissas. After that, take the result. This is the final result. Final result is already in the normal format. When it is in normal format, directly store it. If not in normal format, convert the data into normal format, then store it. Okay, it is already in the normal format, 1.BBB. So that storing into the memory. Take the format, 32-bit format, storing, sign, BE, Mantissa. Mantissa is a fraction, that is the reason zeros padding takes place at LSB. Understood? So that answer is 43D28000. I hope you understand, my dear students. Okay? Alright. Next question is on the screen. All of you, please read the question. Read the question and solve it. Read the question, quick. Tulsiram, you are asking the question, sir, can we align any data to make exponent 0? Actually, why we are making exponent 0? Suppose you want to report the decimal value. At that time, we need to make the exponent 0. Later, take the positional weights to report the binary value into the decimal format. Okay, at that time, we are making the exponent 0. Okay. Tulsiram, do you understand the point? If you want to report the decimal equivalent, then make the exponents 0 by align the data. Okay, but in this question, in the previous question, we are not going to report the decimal value. That is the reason no need to make the exponent 0. Okay, we are going to make the exponent 0 to report the decimal equivalent with respect to the given binary data. Okay, Tulsiram. Very good. Students, I am waiting for your answer. Consider a hypothetical CPU. I am just reading the question. Analyze this. Consider a hypothetical CPU which supports 60 instructions. Total 60 instructions are there. 30 registers are there. And 256 KB memory space is there. It is a hypothetical CPU which supports 60 instructions and 30 registers, 256 KB memory space. Okay. Instruction contain 2 register operands, memory operand, 15-bit immediate constant field. In the instruction, 2 register operands are there, 1 memory operand is there, 15-bit immediate constant field is there. Okay. Program contain 200 instructions. In the program, 200 instructions are there. Okay. How much memory space is required? How much memory space is required? In bytes. We need to report the space in bytes to store the program. Okay. How much memory space is required in bytes to store the program? Program contain 200 instructions. To store 200 instructions, how much memory space is required? That we need to report in bytes. Please solve this question. Yeah. Actually, in this question, there is a possibility to do the mistakes. Student's mistake is there. Okay. Right. Tushar, you given the right answer. Pallav Jain, there is a mistake in your answer. Student mistake is there in the question. Please don't do that mistake, because you know the structure of the memory. When you know the structure of the memory, compulsory you are going to give the right answer only. You know, some students, those who are giving the wrong answers, you know, they misinterpret the structure of the memory. So carefully read the question and try to answer the question. Yes, Srijal Patel given the right answer. Karthik, right answer. Umesh, correct answer. Subhashni, correct answer. Very good. Pallav Jain, now you are right. Lokesh, correct answer. Okay, many students are given the right answer. You see this. Okay. Solution is, in the system 60 instructions are there. Okay, 60 instructions and 30 registers are given. Then memory is 256 KB main memory. Main memory is a RAM. See this, memory is in byte na? See this, memory is in byte. That means cell size equal to 8-bit. This is important. Memory is a byte addressable memory, 256 KB. Cell size is byte, so byte addressable memory. In every cell, 8-bit storage space is present. Okay, that is a structure of the memory, byte addressable memory. Okay, students, all right. Now, here instruction format given. Instruction design or instruction format. Every instruction by default contain opcode. Okay, compulsory opcode is present in the instruction. All right. Now, instruction contain 2 register operands, and memory operand and immediate constant fields. This is the instruction format given in the question. Opcode, register, register, memory, immediate. Opcode size depends on number of instructions present in the system. 60 instructions are there. CPU supports 60 instructions, base 2. How many bits are required? 6 bits. Opcode size is 6 bit. Register. System supports 30 registers. To refer register, 5 bit address required. 30 registers. To refer one register, need of 5 bit address. Okay, memory. Here 256 kilo cells given. To represent 256 kilo cells, how many bit address required? 18 bit address required. Next 15 bit immediate field is given. Okay students, 15 bit immediate field already given in the question. Now add them and report the size. 6 plus 5 plus 5 plus 18 plus 15. What is answer? 49 bit. So total instruction size equal to 49 bit. Instruction size is 49 bit. Now we are going to store the instruction into the memory. 49 bit instruction stored into the memory. How it is stored? So storage structure is like this. Okay, what is the memory? Byte addressable memory. Cell size equal to 8 bit. Okay, so here these are the memory cells. Like this. Okay, cell 0, cell 1, 2, 3, 4, 5, 6, 7, 8 and so on. Memory cells. In every cell 8 bit space is present. 8 bit. Cell contain 8 bit storage space. Alright. Okay. Now store the instructions into the memory. Now I am storing instruction. Instruction 1. What is the size of instruction? 49 bit. So here first cell, second cell, third cell, fourth cell and so on. Okay, 1, 2, 3, 4, 5, 6. Okay, 6 into 8. 48 bit. But instruction size is how much? 49 bit. Therefore, 7th cell is also required. In the 7th cell, 8 bit space is there. So in the 8 bit space, we are using only 1 bit space and remaining 7 bits are unused. Remaining 7 bits are unused. Okay, that unused space we cannot use for second instruction. Okay, once a cell is allocated for instruction, that whole cell is counted for that instruction only. Okay, this concept you read in the operating system as a internal fragmentation. This concept you read in operating system as a internal fragmentation. Okay, so same concept I am using here. Instruction size is 49 bit. Cell size is 8 bit. So when I allocate the memory space to the instruction, okay, total 7 cells required. In the 7 cells, 6 cells are fully utilized the space, and in the 7th cell only 1 bit space is required and remaining space is wasted. Even it is wasted, that cell is counted for that instruction only. Therefore, one instruction takes 7 cells. 7 cells of a storage space required for one instruction. Like this, second instruction 7 cells, third instruction 7 cells and so on. Therefore, program size equal to how many? 200 instructions developed in the program. As a user, I developed the source code with 200 instructions. Number of instructions in the CPU 60. Making use of 60 instructions, I written the program. In that program 200 instructions are there. I hope you understand. Okay, so every instruction takes how much space? 7 cells space. So 200 into 7, that is 1400 cells required. In every cell 1 byte, therefore 1400 bytes storage space is required to store the program. That is the answer. Okay students? Alright. So here program storage space is equal to 200 into 7 cells. This is equal to 1400 cells. In every cell 1 byte is there, therefore 1400 bytes. So this is the answer. Okay, made easy students, they know how to solve this question. Non-made easy students, compulsory they are introducing the wrong interpretation in this question. What is the wrong interpretation? Non-made easy students' point of view. Wrong interpretation is like this. Students are calculated the size like this. Program storage space, that is equal to 200 instructions into 49 bit divided by 8 bytes. Like this they are calculating. Okay, this is the student mistake. Don't do this. This is wrong. Why this is wrong? Because cell size given in the question as byte. When cell size is byte, we are going to allocate only 1 byte storage space in every cell. But here what you did, you are treating every cell is 49 bit. That is the reason 200 into 49 divided by 8 equal to total space. That is the student mistake. Okay, don't do that. Memory cell given as a byte addressable. Cell size is 8 bit. That's what our answer should be, 1400 bytes. Okay students, I hope you understand. Alright. So read the questions carefully and interpret the logic. So answer is 1400 bytes. Yeah. All students given right answer. Shifali, Tulsiram, yeah, Mansi, Rahul. Everyone given right answer. Thank you so much. Then go to next question. Yes, this is the next question, all of you. Read the question and solve the question. Yeah, Tulsiram, Mansi, this is the question related to what? Expand opcode technique, right? So all of you please solve this question, because you know already what is expand opcode technique. Apply that logic, do it fast. Subhashni, answer please. Solve it fast. Okay, right. Now see the question. Students, those who know the expand opcode logic, you please solve it. Those who don't know that expand opcode technique, you please watch the analysis. Okay. So finally, we both conclude the answers, right? See, consider a hypothetical CPU, some example CPU which supports 24-bit instruction. They given instruction size 24-bit, placed in 16 KB memory space. Memory capacity given 16 KB. Then CPU supports 16 registers. Number of registers in the computer is 16. Okay. If there exists 252 to address register reference instruction, what it means? To address instruction, both the addresses are refers the register. Okay, that's what they given, to address register reference instruction. Address 1 is register address 2 also register address. Okay, right. and 1020 one address memory reference instruction. See this? Two address instructions are register reference instructions. One address instruction is memory reference instruction. Okay? There is a clear difference present in the question itself. Right? Then number of zero address instructions formulated in the system is. We need to find out the zero address instructions in the system. Okay? So given is like this. Given information is instruction size, that is equal to 24-bit instruction given. Instruction formats in the computer is two address, one address, zero address. Dear students, three different formats present in the computer. All the three category of instructions are having the same size. Okay, fixed length instructions, different formats. Compulsory expand opcode technique is required. Okay, na? So these are the different formats. All the formats having the same size, fixed length. Two address instruction is 24-bit, one address instruction is 24-bit, zero address instruction also 24-bit. So different formats implemented on a fixed length use the expand opcode technique. Use expand opcode technique. This you know. Okay. So apply the expand opcode technique and solve it. Let me see, is there any student given the answer? Yes. Thank you so much, my dear students. Before my explanation, you already given the answer. Shobit given answer. Right. Rahul given answer. Pallav, correct answer. Vandit, yeah, right answer Vandit. Yeah, every student given the right answer. Mansi, Soumya, Tushar. Thank you so much, my dear students. Okay, it shows your perfection in the concepts, right? When you understand the concept clearly, then you can implement the concept while solving the question. Definitely it will give the right answer only. Okay, so in the GATE exam, frequently asked questions, these all are. Okay, instruction formats, expand opcode techniques, and a floating point storage, floating point retrieval, okay, data range. These all are the common questions because of computer is a real machine, you know, with a fixed architecture. So when it is a fixed architecture, everything is fixed. Terminology is fixed, specifications are fixed, okay. Question formulation is also fixed. Static analysis present in this subject. So formation structure will be same, but a small logics are present inside the question. If you understand the concepts of a computer organization, directly you can implement the concepts while solving the question. So all the students are given the right answer. Right answer is 1024. 1024 is the right answer. Okay, after implementing 252 two address register instructions and 1020 one address memory instruction, 1024 zero address instructions are formulated. That is right answer. Okay, students? Yeah. Those who are already completed the analysis or already solved the questions, you please wait. Okay, let me complete the analysis quickly for other students. Okay. Here, two address format given, students. See this? Two address register reference instructions. Opcode. Both the addresses are register references. This is the two address format, dear students. Instruction size is 24-bit. Register, number of registers in the computer given as 16. 16 registers given in the question. Therefore, 4-bit. 4-bit address. This is also 4-bit. Okay. So 4-bit and 4-bit. And remaining bits are used as a remaining bits are used as a opcode, that is 16 bit. Then one address memory reference instruction. One address memory reference, that is opcode and memory address only. Instruction size given as 24 bit. Memory capacity, what is memory capacity mentioned? 16 KB. Therefore, here 14 bit address, right? Remaining 10 bit is the opcode. Next, 0 address format. In the 0 address format, only opcode is present, there is no address part. So instruction size is 24 bit. This opcode size is also 24 bit. Like this, 3 different formats present. 1, 2, 3. After taking the 3 formats, we need to identify the primitive format. Primitive format means smallest opcode. Smallest opcode instruction is a primitive instruction. So here it is 16 bit opcode, 10 bit opcode, 24 bit opcode. So smallest opcode is 10 bit opcode. Therefore, this one address is a primitive instruction. Okay, first to design the primitive instructions, identify the free opcode, use the free opcodes to design the derived instruction. What is the derived instruction? Next smallest opcode. है ना? Next मतलब क्या है? 16 bit opcode and 24 bit opcode. In this, small is 16 bit. Therefore, to address is a derived instruction. Okay. Now, take the free space from the primitive, design the derived instruction. Later, take the free space from the derived, design the further derived instruction. So, further derived is 0 address. Okay. So, like this, based on the opcode size, we are going to decide primitive, derived, further derived. Okay, students. Maybe some students are having the doubt, sir, here different opcodes are there, different size of opcodes. That's what you separated primitive, derived, further derived. Suppose 2 opcode sizes are same. Assume 2 address instruction opcode is 16 bit, 1 address instruction opcode also 16 bit. Suppose opcode size is same. Then how can you decide the primitive and derived? Answer is, when the opcode size is same, we can decide primitive and derived based on the format. Higher order format is primitive, lower order format is derived. So that 2 address format is higher, 1 address format is lower. Therefore, when the opcode sizes are same, 2 address format is primitive and 1 address format is derived. Okay, students, like that you can decide. But in this question, opcode sizes are different. Therefore, smallest opcode is a primitive. Next smallest is a derived. Next one is further derived. Like this. Okay, all right. Next, please. Simply take the primitive. First, primitive format. Primitive format is 1 address format, opcode and memory address. So memory address is 14 bit, opcode size is 10 bit. 10 bit opcode means number of operations equal to 2 power 10, that is 1024. So 1024 one address memory instructions are possible in the system. But how many are already implemented? In the question, it is given that 1020 one address instructions are implemented. Therefore, number of free opcodes after one address instruction equal to number of free opcodes after one address instruction, 1024 minus 1020. This is equal to 4. See the question. In the question, it is given clearly 1020 one address instructions are already implemented. So that total possibilities 1024 minus implemented 1020. Free 4. 4 opcodes are free. These free opcodes are used for to address instruction. Okay, derived instruction. See this. Number of 2 address instructions possible? How many 2 address instructions possible? Okay, now see this. Here address field size is 14 bit. In the 2 address format, how many bit address we want? 4 bit and 4 bit. Total 8 bit address I want. In the 1 address format, 14 bit address is there. Okay, from the 14 bit address I want only 8 bit address. Okay, take 8 bit from 4 bit and remaining bits are free. How many bits are free? 6 bits are free. So that 6 address bits merged with the free opcodes. Okay, that is number of free opcodes are 4 into 2 to the power of free address bits. How many address bits are free? 6 bits. 2 power 6. This is equal to 2 power 8. That means 256. So 256 2 address instructions are possible in the system. But how many are implemented? That is given in the question. In the question what is given? 252 2 address instructions implemented. Therefore free space equal to number of free opcodes after 2 address instructions equal to 256 minus 252. This is equal to 4. 4 free opcodes are there. These 4 free opcodes used for 0 address instruction. In the 0 address instruction, there is no address part. But in the 2 address format, 8 bit address is there. That 8 bit address I don't want in the 0 address format. So that 8 bit address merged with the free opcode. So number of 0 address instructions equal to free opcodes 4 into how many address bits are merging? 8 address bits. 2 to the power of 8 combinations. This is equal to 2 power 10. That is 1024. Okay. So after implementing the 252 2 address instructions, 1020 1 address instructions, 1024 0 address instructions are formulated in the system. This is the question. This is the analysis of the question. So solution is 1024. I hope you understand. Many students are already given the right answer because they are the made easy students. If any non-made easy student is there, non-made easy student watching this, that student compulsory identify the analysis procedure to solve the question. Okay, this is the analysis. This analysis is called as the expand opcode technique. This is the expand opcode technique. First go to primitive format, okay, identify the free space, okay, design the derived instructions, identify the free space, design the further derived instructions. Okay, so by merging the address field with a free opcode, opcode size will be increased. See this, here 10 bit opcode is there. By merging the 6 bit address, okay, to the 10 bit opcode, opcode size is increased to 16 bit. Okay, next by merging the 8 bit address, here opcode size is increased to 24 bit. So address field will be merged to free opcode to design the further instructions. Okay students, I hope you understand. Thank you. All the students are given the right answers. Very good. Now go to the next question. Students, this is the next question. Please concentrate on the question, give the answer. Do it fast. Addressing mode question it is. Students, I hope you understand the way of analyzing the question. First instruction format question, expand opcode technique question. This is addressing mode question. We don't want to miss any concept of the computer organization. Okay? Answer please. Yeah, Mansi, you are right. Sifi, Shifali, you are also correct. Answer please. Vandit. Vandit given the right answer. Thank you, Vandit. Shakir. Shivani, right? Mansi, correct? Shobit, correct? Very good. So, students already given the right answers. Let me read the question. Question is what? Consider the following and identify the correct statements. Okay, we need to identify correct statements. First, immediate addressing mode. See this. Immediate addressing mode is used to access the unsigned or signed constants. Is it true or false? Okay. Everyone knows that immediate addressing mode is used to access the constants only. Okay. This is a correct statement. When instruction is designed with a immediate addressing mode, address field itself contains the data. Okay, instruction is designed with a immediate addressing mode, address field itself contains the data. That data may be unsigned data or signed data. Therefore, immediate addressing mode is used to access the constants. This is true. Correct statement. Next. In the indexed addressing mode, effective address, EA stands for effective address. AM means addressing mode. In the indexed addressing mode, effective address is generated by adding the constant to content of some register. Effective address is calculated by adding the constant value to content of some register. This statement is also true because in the indexed addressing mode, constant is acting like a base address, register is a index register. Therefore, index value will be added to base address to calculate the effective address. So second statement is true. Third statement, in the absolute addressing mode is called as direct addressing mode. Okay. In the direct addressing mode, data is present in the register. This statement is false because in the direct addressing mode, data is present in the memory. Data is present in the memory, not in register. Okay, that's what this statement is false. Next, in the memory indirect addressing mode, effective address is present in the register. Memory indirect addressing mode. See this? Memory indirect addressing mode. Effective address is in the register. This statement is false. Why? This is memory indirect, na? See this? Memory indirect. Memory indirect means effective address is in the memory. Register indirect means register indirect. Effective address is in the register. You know the difference between memory indirect and register indirect. Okay, that is the reason this statement is false. Memory indirect addressing mode stands for effective address is present in the memory, but here they given wrong statement. Effective address is in the register. That's what it is false. So correct statements are A and B. This is right answer. You know, correct statements A and B. Students, I hope you understand. Okay, all right. Next question, please. Yeah, this is the next question. Students, please read the question. Consider the following statements and identify the correct statements. Identify the correct statements. All of you, please do it fast. What is the right answer? Shivani, you are correct. Vandit, wrong answer. Read the statements. Please read the statements. Shivani, you are given right answer. Vandit, wrong answer. Pallav Jain, wrong answer. Tulsi Ram, wrong answer. Tushar, correct answer. So, my dear students, you please be careful with the MSQs. Multiple selection questions are always creating the confusion. So that you please read all the statements carefully and select the correct answer. Okay, so MSQ questions are tricky questions. So you need to decide whether that statement is right or wrong, right or wrong. Multiple statements may correct or multiple statements may incorrect. So if you know the total concept, then only you can able to select the multiple selections. So MSQ questions are tricky questions in the GATE paper. So please practice MSQ questions, and please refer all the concepts. Don't miss any concept in any subject. Okay, right. Now look at this first statement. When the micro instruction is designed, see this, micro instruction is designed with 100 micro operations, then it takes 100 cycles to complete. Okay, is it true or false? This is false statement. Why? You know that micro instruction is designed with one or more micro operations. It takes one cycle to complete because all the micro operations running in parallel. Okay, inside the micro instruction we may design 1000 micro operation. Still it is taking one cycle only because all are running in parallel. That is the reason micro instruction takes only one cycle. Inside that micro instruction there may be one micro operation or more than one micro operation. Still it is taking one cycle only. That is the reason first statement is false. Second statement, micro operation takes one cycle to complete its execution. Yes, this is true. One cycle based operation is a micro operation. You know the basic definition. Very nice. Next, when the micro instruction is designed with 100 micro operations, then it takes one cycle to complete. Yes, this is true because these 100 micro operations are running in parallel. When they are running in parallel, it is taking only one cycle. Next, in the CPU control unit design, IF, ID, OF, PD, WB are the common micro programs to complete the instruction processing. You tell me, is all our common micro programs for all the instructions? No. Okay, IF is common, ID is common, OF is common, WB is common, but PD will be varies. You know this, PD, process data varies. With respect to opcode, suppose opcode is a addition related microprogram to process. Okay, opcode is a multiplication related microprogram to process. Therefore, depends on the opcode, PD will be varies. PD microprogram is not a common microprogram in the instruction design. In the instruction execution process, instruction fetch is a common process, instruction decode is a common process, operand fetch is a common process, operand store is a common process. But processing data is not common because of the operations are different. So different operations के लिए different micro programs are required. Okay students, therefore this statement is false. Okay, some students are given this statement as true, but this is not a true statement. Why it is not true? PD is not a common microprogram. PD microprogram varies instruction to instruction. Therefore, PD is not a common microprogram. So this statement is false. Okay, so correct statements are B and C. Okay students, many students are given the answer B and C. Some students are given the answer B, C, D. D also given as a right answer. Okay, some students, but that is not correct. D is wrong because of PD, process data, is not a common microprogram for all instructions. Okay, according to the opcode, processing will be changed. Okay, I hope you understand. Is it clear, dear students? All right. Now, go to the next question. Students, next question is on the screen. All of you, please read the question and solve it. I am waiting for your answer. Very good. Srijal, you are right. Sir, PD is not a common micro program. Yeah, you are correct, Srijal. Pallav Jain, operand fetch is common, right? For every instruction, operands are required. Maybe direct addressing mode, indirect addressing mode, register addressing mode. So that operand fetch is a common process. Yeah, instruction decode is a common micro program. But processing data will be different. Very nice. Now this is the next question. All of you please read the question, give the right answer. Because now pipeline questions are going to be started. Please be careful and try to give the right answer. I am waiting. Oh. Who? Shobit. Shobit, you given right answer. Sauvik also. Sauvik Sarkar, given right answer. Pallav Jain, you are saying that halt. Okay, it is a halt instruction. Halt instruction is what? Branch instruction. Branch instruction ke liye instruction fetch is common, instruction decode is common. Okay, it does not require operand fetch. Okay, does it mean that when operand fetch is not required, can we take the different operand procedure? No. When it is not required, we just leaving it. Okay, separate procedure is not taken. That is the reason operand fetch is common micro program. If it is required, you can use it. Otherwise, don't use. Okay, Pallav Jain. Subhashni, correct answer. Vandit, correct answer. Very good. All the students are given right answer. That means you are perfect in the pipeline. Let me see whether you are perfect or not in the next question. This is an easy question. In the easy question, you can easily answer the question. Okay, in the next question, I am going to see your perfection in the pipelining. Very nice. Now see the question, my dear students. Usually in the classroom, I explained the uniform delay pipeline, non-uniform delay pipeline. Okay, आपको याद है क्या? Do you remember that? Uniform delay, non-uniform delay pipeline, I explained in the classroom. Okay, at the time of analyzing the pipeline in the classroom, I given only one thing, that is uniform delay buffers. But in this question, see this is hypothetical pipeline. Hypothetical. In this pipeline, they given the stages with different delays. They given the buffers with different delays. So what it means? Non-uniform delay stages with non-uniform delay buffers. Then how to solve the question? Okay, that we will see. Understood? Right. See this. Consider following pipeline used to execute the program which contain 400 instructions. 400 instructions are present. Okay, this is the pipeline given. Now, first report. What is the K value? K is equal to 5. Number of stages, 5 stages. N is equal to how much? 400. You know this. 400 is a finite number. When the N is finite, we are using the formula, that is execution time of the pipe equal to K plus N minus 1 into TP. This is the formula, K plus N minus 1 into TP. What is TP? Cycle time of the pipeline. See this. TP equal to maximum of stage delay plus buffer delay, together maximum, not individual. This is the formula which I explained. Stage delay plus buffer delay together. So see this, maximum of, okay, stage delay, this is 8, buffer delay 2, total 10 nanosecond. 10 nanoseconds के बाद S1 output is given as input to S2. 10 nanoseconds के बाद S1 output become input to S2. Next, S2 6 plus 1. 7 nanosecond. 7 nanoseconds के बाद इसका आउटपुट बिकम इनपुट टू S3. नेक्स्ट 4 plus 3 7 nanosecond. 7 nanoseconds के बाद S3 आउटपुट बिकम एज इनपुट टू S4. S4 5 plus 4 9 nanosecond. After 9 nanoseconds S4 output become as input to S5. Next S5 8 nanosecond. In this question they given buffer also. Question में buffer is given at the end of last stage, then take that buffer. If buffer is not given at the end of last stage, no need to take the buffer, but here given, so that take it. If not given, don't take that. Okay, right, here given, what is its delay? 3 nanosecond. 8 plus 3 11 nanosecond. After this output will be available. Output will be available. Okay na? So this is the cycle time analysis. Okay, maximum of stage delay plus buffer delay. Now max of, tell me max of this means what will be the answer? 11 nanosecond. Now TP is 11 nanosecond. Substitute that 11 in this formula. K is 5, N is 400 minus 1 into 11 nanosecond. Compute this. 5 plus 400 minus 1 into 11. Answer please. 4444 nanoseconds. This is the answer. 4444 nanoseconds. Okay. Now go to the option. Select the answer. What is answer? B is the right answer. All students are given the right answer. Okay. So in this question there are multiple confusions present. Some students are not taking the last stage buffer. So that student answer is different. Some students are taking the individual stage maximum delay, individual buffers maximum delay. They are adding maximum buffer delay plus maximum stage delay. That student answer is different. Okay. So different students are giving the different answers based on their own interpretation. But correct interpretation is this. Correct interpretation is this. So in this interpretation, TP become 11 nanosecond. Answer become 4444 nanosecond. Answer is B. I hope you understand. Is it clear, my dear students? Very good. Now go to the next question. I want to see the correct answer. Okay? Go to the next question. Yes, this is the question. Usually 2 marks weightage question. So you please read the question and solve it. Do it fast. Yeah, Mansi, Ratnesh, Vandit, you all are given the right answer. Okay, Shrijal. Shakir Ali saying that, sir, why buffer is given at the end of last stage? This is a hypothetical pipeline. Question may they given hypothetical pipeline to test the students' knowledge. Okay. Usually in the real pipelines there is no buffer at the end of last stage. Okay. In the classroom I explained the risk pipeline. Am I added any buffer at the end of last stage? No. So in the real pipelines no buffer at the end of last stage. But in the question they given customized hypothetical pipeline. You know? So according to question we need to answer, right? Shakir, got the point? Very good. Any other students? Any doubts? No doubt. Okay, now read this question and solve it. Usually 2 marks weightage question. Mansi, please give the right answer. Okay. Ajay. Ajay, you given the answer, but that is partially correct. That is operand forwarding question you given without operand forwarding. Okay. Right, students. See this 5-stage pipeline. Students, those who know the concepts, you please solve it. Okay. Let me explain simultaneously. Right. IFID EXMAWB. 5-stage pipeline they given. Cycle time also given 2 nanoseconds. Use it to execute the following code. This code is executing. All instructions are spending 1 cycle on all stages. All stages में 1 cycle. But load instruction takes 4 cycles on 4th stage. ALU instruction takes 3 cycles on 3rd stage. Okay, right. This is the program. Time saved to execute the program using operand forwarding over without operand forwarding. That means we need to execute the program with operand forwarding and also without operand forwarding. Then later identify the time save. Okay, students? All right. So here IF, ID, EX, MA, WB. Okay. So I1, I2, I3, I4. 4 instructions. All right. Every instruction taking 1 cycle on all the stages. Okay. But load instruction spending 4 cycles on 4th stage. So I1 is load. So 4 cycles on 4th stage. I2 is load. 4 cycles on 4th stage. I3 is add. ALU instruction. 3 cycles on 3rd stage. It is 3 cycles. Then multiplication 3 cycles. And remaining 1 only, like this. All right. Okay, so this is the given information. Now decide the dependencies. Dependencies. I2 inputs, I1 outputs matching? No. Therefore, there is no dependency between I2 and I1. I3 input. Compare with I2 output. Matching? Yes, matching. Therefore, I3 dependent on I2. Very nice. Next, I4 input. I3 output. Matching. So, there is a dependency between I4 and I3. Okay. I3 dependent on I2, I4 dependent on I3. There is no dependency between I1 and I2. All right. Now, draw the cycle diagrams. Without operand forwarding, with operand forwarding. Okay. Okay, clock cycle, CC1, CC2 and so on. All right. Now execute the instructions. I1, I2, I3, I4. 4 inputs. Okay. X-axis indicating the cycles, Y-axis indicating the inputs. Allocating the stages. Allocate, please. First IF, then ID, IF, EX, ID, IF. You know this. Thomas law algorithm is applicable to the ID stage. So here Thomas law algorithm is applicable. This is not dependent on, I2 is not dependent on I1. Okay, so directly moving to MA. This is moving to EX. This is moving to ID. Next is moving to IF. See this, I1 taking 4 cycles on MA. Okay, so that memory stage is busy. When MA is busy, this is waiting on EX. This is waiting on ID. Okay, this is waiting on IF, like this. Okay, students? Alright. After that, I1 is moving to WB. Okay, I2 is waiting for stage, not for data. So no operand forwarding between I2 and I1. No operand forwarding because no dependency. I2 is waiting for stage. Stage is available here. So take the MA. Take the MA. Got the point? My dear students, you know that this I3 is dependent on I2. You know this. Dependency detected, na? I3 dependent on I2. But I2 output is not available in the EX buffer. Some students are taking from here. But this is not the data. This is the effective address. Because of the I2 is a load instruction. Load instruction output is available in the MA stage. So MA stage taking how many cycles? 4 cycles. Okay, like this. After 4 cycles, this buffer contains the data. Now this data you can forward here. That data forwarding there. Okay, so up to that, this is waiting. I3 waiting on ID. ID and ID. Okay, so this is waiting on IF. IF, IF, IF. Okay, after that, it is proceeding into WB. This is coming into EX, execution, and this is coming into ID. Now Thomas-Rowe algorithm is applicable. Data dependency detected. So I4 is data dependent on I3. Okay, I3 status present in EX stage. EX stage taking 3 cycles. Okay, 3 cycles के बाद output available here. That output you can forward. Maybe some students are having the doubt, sir, why you are taking the data from EX? Because EX buffer contain the data. MA buffer contain the data for load instruction. When instruction is load, MA buffer contain the data. When instruction is ALU instruction, EX buffer contain the data. You know the meaning of that. Okay, right. So that it is waiting on ID, waiting on ID. Very good. Next MA. This is EX. Correct? Next WB. This EX taking 3 cycles. इसके बाद MA. Next WB. Okay, students. So total how many cycles required? 19 cycles. 19 cycles. Into each cycle time is 2 nanoseconds. Execution time. 19 cycles into 2 nanoseconds. That is equal to 38 nanoseconds. This is the time required to execute the program with the operand forwarding technique. Okay. So this we can easily calculate like this. 4 instructions. I1, I2, I3, I4. Very good. Usually every instruction taking 1 cycle. Every instruction taking one cycle. Overlapping के कारण. Okay. But here I1, 1, 1, 1, 4, 1. So usually it is taking 1 cycle. But this MA stage is taking 4. Therefore here 3 extra cycles needed. Three extra cycles. Okay, right. I2 is also usually taking 1 cycle. Very good. 1 cycle. But how many extra cycles required here? This is 1, 1, 1. This is 4. This stage is taking 4. Okay, how many cycles extra required? Maybe you are saying, sir, 4 minus 1, 3. 3 cycles required. But there is a data dependency occurred between I3 and I2. Data dependency. This data dependency accepting the data at the end of the MA stage, not at the end of EX stage. Usually it is expecting the data from EX stage. यहाँ से data expect कर रहे. But it is getting the data from where? MA. So how many cycles it is waiting? See this? How many cycles? 4 cycles, na? Right. Take 4 extra cycles. 4 extra cycles it is waiting. Then I3. I3 के लिए 1 cycle. Then after that, here 3 cycles. See 3. 3 means how many extra cycles are present. Okay. That depends on the dependency also. But I4, I3 both are dependent. This dependency taking the data from where? EX buffer only. So how many stages it is waiting? Only 2 stages. So here 2 extra cycles. Okay. I4 1 cycle plus here it is taking 2. ये देखो 3. 3 से we are taking 1 as a common, extra 2. Okay, total count 4 plus total how many? 15 cycles. 15 cycles means 15 inputs. In every 1 cycle 1 input is there, so that 15 cycles means 15 inputs. Now apply the formula. K plus n minus 1. Okay, cycles. So K value is how much? 5. 5 plus 15 minus 1. This is equal to how many? 19 cycles. Okay, like this also you can able to calculate the number of cycles. With the diagram, if you want to calculate, you please solve the question using the diagram. This is manual procedure. Once you get the perfection, directly you can conclude like this. Every instruction usually taking one cycle. Okay, apart from 1 cycle, how many extra cycles are required? That depends on the table, this table. Depends on the table and depends on the dependencies, you can decide extra cycles. Now calculate the total number of cycles. In every cycle 1 input is there. Therefore 15 cycles means 15 inputs. K plus n minus 1. 5 plus 15 minus 1. Total 19 cycles. Okay, this is the optimized way to identify the number of cycles without diagram. Okay students, you please practice like this also. Once you get the perfection. Without perfection, you cannot get this analysis. You know, first get the perfection in that area, later go to the optimized analysis. Okay, this is about the with operand forwarding. Now without operand forwarding, you know this? Without operand forwarding means we are taking the data after WB. After WB reading the data. Okay, now see this, instruction 3 dependent on instruction 2. So it is taking the data from here, ID, all of you. It is taking the data here. After WB, it is reading the data. Here it is reading. So how many extra cycles? 1, 2, 3, 4, 5, 6. 6 extra cycles with respect to I2. Then I3 के लिए देखो, after WB, it is reading the data. Here it is reading. Here it is reading means what? How many extra cycles? 1, 2, 3, 4, 5. 5 extra cycles. Okay. After that EX, 3 cycles means it is taking 2 extra cycles and first one taking 3 extra cycles. So without operand forwarding, we can calculate like this. I1, I2, I3, I4. Every instruction usually taking 1 cycle, 1 cycle, 1 cycle, 1 cycle. Plus I1, MA 4 cycles. Therefore, when we are taking 1 as a common, extra 3 cycles are there. 3 extra cycles. Very good. Next, I2. I3 to I2, there is a data dependency. That data dependency accessing the data after completion. After completion means here. Here it is accessing the data. Therefore, how many? 1, 2, 3, 4, 5, 6. 6 extra cycles. Okay. Plus, Then I3 के लिए one cycle is common, but there is a dependency between I4 and I3, so that I4 is accessing the data after completion of I3. Okay, so kaha? Here. After completion of I3, here it is accessing the data. Therefore, how many stalls? 1, 2, 3, 4, 5. So 5 extra cycles. Okay, right. Next I4. I4 EX stays taking 3 cycles. Therefore, 1 is common. Okay, so from the 3, 1 is common means extra cycles 2. 2 extra cycles. Okay, so total how many? Count it. 4 plus 3 plus 6 plus 5 plus 2. That is 20 cycles. Okay, 20 cycles means n equal to 20. Now apply the formula k plus n minus 1. K plus n minus 1 cycles. Okay, this is equal to k value. How much? 5 plus n 20 minus 1 cycles. This is equal to 24 cycles. This is the without operand forwarding. Without operand forwarding analysis is this. Okay, without diagram, I can able to calculate number of cycles required without operand forwarding. Okay, 24 cycles. If you want to see the proof, then calculate manually. Okay, calculate manually. Let me draw that also, because proof के लिए, if you want to see the proof, like this. So total 24 cycles I taken. This is without operand forwarding. Okay, execute the 4 instructions. How to execute? We'll see. I1, I2, I3, I4. 4 inputs. Right? Proceed. This is IF, ID, IF. Okay. Then EX, ID, IF. Okay. Then this is MA. Here it is EX, because there is no dependency between I2 and I1. So ID, IF. Okay, so this is taking 4 cycles, MA, MA, MA. Okay, up to that, this is waiting on EX. This is waiting on ID. This is waiting on IF. Very good. Next, please. This is moving to WB. Okay, now this is moving into MA. This is coming into ID only. This is into IF only. Why? This is data dependent on I2. So first complete the I2. I2 complete it. 4 cycles on MA, then WB. Here I2 completed. So once I2 execution is completed, then here it is reading. You know this? Here status, this is read the data after write. Here status of this instruction is 1. Status 1 means execution completed. Once execution is completed, read the data after write. Without operand forwarding means read takes place after WB. Okay students, you know this. So this is ID, 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 ID. So this is waiting on IF only. IF, IF, IF. Very good. Now it is moving into execution. Now this is coming into ID. Now it identifies the dependency. I4 data dependent on I3. So complete I3 first. So EX 3 cycles, next MA and WB. Here completion. After completion, read the data. Reading takes place here. Read the data after the write operation. This is read. Status will be 1. So when I3 status is 1, you can read the data after write. Very good. Up to that, this is waiting on the ID stage. ID. Now moving into EX stage. 3 cycles. Next MA. Next WB. See this? How many cycles total? 24 cycles. This 24 I already calculated na? Okay. How I calculated? You know. This is taking the 3 cycles extra and this is see this. Here it is reading the data here. Okay. Actually it is supposed to read from here. But it is reading here. How many cycles? 1, 2, 3, 4, 5, 6. These are the 6 stalls. Okay. But this instruction reading the data here. But actually this is supposed to read from here. How many? 1, 2, 3, 4, 5. Okay. I1 के लिए 3 extra cycles, I2 के लिए 6 extra cycles, I3 के लिए 5 extra cycles and I4 के लिए 2 extra cycles. 2 extra cycles means for EX के लिए. Okay. Total 24 cycles. Got the point? All right. So here execution time equal to 24 cycles into 2 nanoseconds. This is equal to 48 nanoseconds. This is the execution time. Okay na? Now time save equal to without operand forwarding 48 nanosecond, with operand forwarding how many? 38 nanosecond. 48 minus 38 nanosecond. Total time is equal to 10 nanosecond. 10 nanosecond time is saved. Okay students, I hope you understand. Like this, identify the operand forwarding questions. Okay, I explained the manual procedure. I also explained the optimized procedure. Okay, think about this question. Okay, watch it again if you have any confusion. Okay, but answer is 10 nanoseconds time is saved. Okay, let me see how many students are given the right answer. Yeah, Mansi, you are saying that sir clear. Vandit. Yeah. Given 10 nanoseconds. Very nice. Tulsiram, 10 nanoseconds. All right. Shivani, thank you. See, dear students, after practice the set of questions, you may get the perfection and you can directly count the number of cycles. By watching the question, you can count the cycles. Okay. First practice manually like this, then count the cycles. Every instruction के लिए one cycle is common. And if any stage is taking more than 1 cycle, then extra cycles are coming out. Calculate the extra cycles. At the time of calculating the extra cycles, you need to check the dependencies between the instructions. And that dependency between EX and ID forwarding, no issue. When it is a MA forwarding, compulsory some extra cycles are created. Okay students, I hope you understand. And if any confusions, you please watch it again, no issue. Now go to the next question. Solve this question. Let me see how many of you are giving the right answers for this question. Do it fast. Usually these are 2 marks questions, you know, time taking process, but after set of questions practice, you may get the complete perfection. Okay, all right. Vandit, you are asking this question, right? This one. Sir, why you are taking 4 extra cycles? This one you are asking, right? This is taking 4 extra cycles. It is, we are calculating 4 extra cycles because I2 will be producing the data for the I3 after 4 cycles. You know, after these 4 cycles, I2 data is available for I3. After 2 cycles, I3 data is available for I4. Got my point? After 4 cycles, I2 data is available for I3. After 2 cycles, I3 data is available for I4. Okay, na? Like that. Okay, Vandit? Clear na? Alright. Similarly, you see this also. Without operand forwarding. What it means? After 6 cycles, I2 data is available for I3. After 5 cycles, I3 data is available for I4. I4 is a final instruction. These 2 cycles, because of EX stage is taking 3 cycles, that's what 2 extra cycles. I1 is always independent. Waha 3 cycles. Why 3 cycles? Because MA stage is taking 4 cycles. इसलिए I1 के लिए 3 extra cycles. Last I4 के लिए 2 extra cycles. But I2 and I3, I2 taking 6 cycles to make its data available for I3. I3 takes 5 cycles to make its data available to I4. Like this. Okay, students? Vandit, I think you got the point. You know? Your issue resolved. Okay? Alright. Students, what is the answer to this question? Very good. Mansi, what is the answer? Vandit given the answer. Let me see whether your answer is right or wrong. Vandit? Mansi? Subhashni, answer please. Yeah, see this, students. Question is, consider 4-stage pipeline with a respect to delays of 2 nanosecond, 4 nanosecond, like this, 2 nanosecond. Use it to execute the program segment which contain 30 load instruction, 60 ALU instruction, 40 branch instruction. All instructions are spending 1 cycle on all stages. Every stage में 1 cycle. Okay. Load and ALU instruction outputs are available in the 3rd stage. Load instruction output, ALU instruction output available in the 3rd stage. Okay. Operand forwarding already used in the pipeline. They given operand forwarding is used. When operand forwarding is used, data dependency stalls are not present. Why not present? EX stage data immediately accessible into ID stage. Okay. Right. Now, branch instruction output is available in the 4th stage. 4th stage mein branch instruction output is available. Very good. Then, what is the program execution time when it is executed in the pipeline without branch prediction? Tell me, students. Without branch prediction means target address is not present in the 1st stage. Without branch prediction means target address is not available in the 1st stage. Where it is available? Given in the question, target address is available in the 4th stage. When it is available in the 4th stage, branch penalty equal to 4 minus 1, that is 3 cycles. 3 cycles branch penalty. Okay, so there is no stalls from the load instruction from the ALU instruction because of operand forwarding is already present. Okay, original program is not given, therefore there is no stalls created with respect to load with respect to ALU instruction. Stalls are created only with respect to branch instruction. Okay students, all right. So find out number of inputs equal to, okay, 30 plus 60 plus 40. Total how many? 130. Okay, next. Number of stalls per instruction. Okay, number of stalls in the program, not per instruction. Number of stalls equal to 30 instructions into 0 stalls plus 60 instructions into 0 stalls. No stalls from load instructions, no stalls from ALU instructions because of operand forwarding is already present in the pipeline. EX stage to ID stage forwarding means no stalls present. You know that. Next please. 40 instructions are branch instructions. Create 3 stalls. Every branch instruction creates how many stalls? 3 stalls. Because target address available in the 4th stage. So number of inputs how many? This is number of stalls 120 stalls. So total inputs equal to 130 plus 150, sorry 120, that is equal to 250 inputs. Number of inputs are finite. When inputs are finite, directly we can apply the formula that is equal to k plus n minus 1, k plus n minus 1 into TP. This is the formula. K 4 plus 250 minus 1 into cycle time. Cycle time depends on the stage delays. Maximum stage delay 6 nanosecond. So apply 6 nanosecond here. Right? Calculate this. 4 plus 250 minus 1. Okay, into 6 nanosecond, that is 1518 nanosecond. This is the execution time of a program. Okay students, no stalls from load, no stalls from ALU instruction, stalls from branch. Okay, so 40 instructions are branch, every branch creates 3 stalls. So total inputs 130 plus 120. This is the way of solving the question. Hope you understand. Okay, let me see who is given the right answer. Very good, yeah. Vandit given right answer, Rahul given right answer, Shivani, Mansi, yes. Feeling very happy, dear students. You know, because when question is like this, then you are applying the existing concepts, what you learn in the classroom or what you learn in your preparation. Okay, so those concepts you are implementing. That's what you are giving the right answers. Okay, thank you. Right, go to the next question. Students, read the question quickly. Subhashni given right answer. Very good. Sobit, Mansi, Shivani, Karthik, Tulsiram. You all are given right answer. Very nice. And what about this question? Okay, just read the question. Consider the following memory specifications. Levels given, 3 levels. Accessing time given per word. This is the word accessing time. Word accessing time. This is hit ratio, 0.7, 0.9, 1. Level 1 hit ratio, level 2 hit ratio, level 3 hit ratio given. This is data transferred between the levels. Okay, word transmission, block transmission, page transmission given. Very good. Word size of the system is 32-bit. Word length of a CPU is 32-bit. Okay. If the data is not in level 1 memory, then 4 word block is. Okay. What is the block size? 4 words. Transferred from L2 to L1. If not in L2, then 8 word page. 8 word page. Okay. That means page size equal to 8 words. Okay. Transferred from L3 to L2. And block is transferred from L2 to L1 and word is transferred from L1 to CPU. What is the average memory access time? Students, you know this as a hierarchical memory organization. Okay, you know the formula of hierarchical. Directly apply the formula and solve the question. Okay, all right. First, T1, level 1 accessing time. One word accessing time, 40 nanoseconds only. Level 2 accessing time. You know, in the level 2, one word accessing time is 100 nanosecond. Block is having 4 words, therefore 400 nanosecond. Level 3, one word accessing time is 200 nanosecond. Page contain 8 words, therefore it is equal to 8 into 2, 1600 nanoseconds. Okay. Now hit ratio given, accessing times already identified. Directly you can apply the hierarchical formula. Formula please. T average equal to H1 into T1 plus 1 minus H1 into H2 into T2 plus T1 plus 1 minus H1 into 1 minus H2 into H3 into T3 plus T2 plus T1. Okay. Now substitute the data and calculate the value. Okay, compute it. What will be the answer? Substitute the data. Compute this. Answer please. Yeah. Mansi, yeah, given the right answer. Shobit also. 208. Vandit, correct answer. Yeah, Subhashni, right answer. Very good, dear students. Questions are a bit lengthy. Okay. But when you know the concepts, directly you can apply the formulas. See, previous questions also a bit lengthy questions. But conceptually, when you are strong, then directly you can answer the questions within a less time. Okay, damn sure that you are compulsory giving the right answers, especially CO subject ke liye. Okay, be perfect with the concepts. Automatically you can answer all the questions. Very good, Tulsiram, you are right. Correct answer. Very nice. Go to next question. Students, see this question. See the question. All of you read the question quickly. Solve it. Okay, what is the question states? Consider 8-way set associative cache 64 KB organized into 32-byte block. Okay, cache data is a subset of 2 power 28 byte. Following main memory addressed data is accessed in the program. Okay, this data accessed in the program. 2 words accessed. Word 1 address is this, word 2 address is this. These 2 words accessed in the program. Okay, word 1 mapped into a cache set denoted as X. Okay, first word mapped into cache set that is denoted as X. Second word mapped into cache set that is denoted as Y. What is the value of X minus Y? Then what we need to do? We need to identify the set number where the first word data is mapped. Then find the set number where the second word data is mapped. Now take the difference. That is the answer. Okay, easy one. What is the answer? Tell me. Let me see. This is 8-way set associative cache. Cache memory size given 64 KB. Block size given 32 byte. Main memory size given. You know this. Cache memory data is a subset of main memory data. So main memory size indirectly given, that is 2 power 28 byte. Therefore, main memory address equal to 28-bit address. Alright. Now, see this. Number of lines n equal to cache memory size by block size. That is 2 power 11. Next, number of sets S equal to n by p way. N value 2 power 11, p value 8. This is equal to 2 power 8. Okay, students. Now address format. Take the address format. 28-bit address divided into tag, set offset and word offset. Word offset depends on the block size. Block size given 32. Therefore it is 5-bit. Set offset depends on the number of sets. 2 power 8 sets. Okay. So that 8-bit set offset. And remaining bits are used as a 28 minus 13. Remaining 15 bits are used as a tag. Okay, so find out the set number 1. Okay, first word address is what? FC B8 B7A. Now interpret this into binary. F C B 8 B 7 and A. Interpreted. Okay. So 5 bits used for word offset. Then 1, 2, 3, 4, 5, 6, 7, 8. 8 bits are used for set offset. Okay. Remaining bits are tag. Now identify the set number where it is mapped. Set number please. This is 1, 2, 4, 8, 16, 32, 64. Take the positional weights. Identify the set number. 64 plus 16 plus 8 plus 2 plus 1. That is 91. base 10. Okay. So first data, first word mapped into cache memory set 91. Now similarly go to the W2. W2 second word. What is the address of the second word? EF given EF DA 6BC. Now interpret this into binary. E 1110 F D A 6 B C. Okay, interpretation. Five bits used for word offset, then 8 bits 1 2 3 4 5 6 7 8. 8 bits used for set offset, and remaining bits are the tag bits. Now identify the set number 1 2 4 8 16 32. So 32 plus 16 plus 4 plus 1, this is equal to 53, base 10. Okay, first word mapped into 91 set, second word mapped into 53 set. Okay, 91 minus 53, that is equal to 38. X minus y equal to X 91 minus Y 53. This is equal to 38. Answer is 38. Okay. How many of yours answer is matched? Let me see. Answer is 38. First word mapped into set 91. Second word mapped into set 53. Decimal values. Take the difference. Difference is 38. Yes. Again, all students are given right answers. Very nice. Thank you so much, my dear students. Correct answers. You given right answers. You know? So conceptually you are very strong, I think. Very good. Fine? Right. Next question, please. This is the next question. Please solve it. Question, please. Consider, see the question. Students, simultaneously you please practice the question. Okay, finally we will conclude the answers. Okay, consider 32 KB direct mapped cache, direct mapping, organized into 32 byte blocks. CPU generates 23-bit physical address. Very good. Cache is updated. Cache is updated with a 16-way set associative. Okay. Direct cache memory updated with a 16-way set associative structure with the same block size. Capacity same, block size same, but structure is changed. Direct cache changed to 16-way set associative cache. Okay. Number of tag bits increased in the tag space of each line in the set. Each line in the set associative cache set is. We need to identify how many tag bits are required in the tag space of a direct cache, how many tag bits are required in the tag space of a set associative cache. Okay, now compare them. Then you can understand how many bits extra required in the set associative cache tag space. Okay, students? All right. Now, solve this. Cache memory. This is the direct cache. Cache memory size, how much? 32 KB. Block size, given 32 bytes. Okay. Then main memory address size given 23 bit. Everything given in the question. Now identify the number of lines. Cache memory size by block size, 32K by 32. This is equal to 1K, number of lines. Now address format please. 23-bit address format, tag, line offset, word offset. This is the direct mapping address format. Word offset depends on the block size. So log 32 base 2. This is equal to 5 bit. Then line offset depends on number of lines. Log 1 kilo base 2. This is 10 bit. Okay. And remaining how many bits? 23 minus 15. That is 8 bit. 8 bit tag space. So that means in every line 8 bit tag space is required. In every line of a cache 8 bit tag space is required. This is about the direct cache. Come to the set associative cache. This is 16-way set associative. So already we know that number of lines equal to 32K by 32. That is 1K. Very good. Next number of sets equal to N by P way. 1K by 16. That is 2 power 10 by 2 power 4. That is 2 power 6. Okay, right. Now address format. Tag, okay, set offset, word offset. This is 23-bit address. Block size 32 byte, 5 bit. And number of sets 2 power 6, 6 bit. And remaining how many bit? 23 minus 11. That is 12 bit. 12 bit tag space. What it means? Every line of a set contain 12 bit tag space. Like this, in every set 16 lines are there. You know, 16 way. 16 way matlab, in every set 16 lines are there. In every line of a set contain 12 bit tag space. Okay, so here 12 bit tag space in every line of a set. Here 8 bit tag space in every line. Okay, then how many bits are increased in the set associative tag space? That is 12 minus 8. Number of tag bits increased. Equal to 12 minus 8. This is equal to 4 bit. So in the set associative cache, 4 bit extra space is required in every line compared to direct cache. Okay students, let me see how many of you given the right answers. Yeah, again all are given right answer. Very good. Vandit, Anuj, Shobit, Rahul, Mansi, Tulsiram, Rajdeep, Sonu. You all are given right answer. 4, 4, 4, 4. Very good. Subhashni. Subhashni also given right answer. Very nice. Okay students. Yeah. See the last question. This is the DMA related question. Students, all of you read the question. DMA related question. See this. Consider 1 kbps IO device, given 1 kbps IO device, interface to 32-bit CPU in a cycle stealing mode of DMA. You know DMA concept. Without CPU involvement, data will be transferred from IO to main memory. Therefore, in the DMA, CPU present in 2 states. One is busy state, second is blocked state. Okay, CPU busy until IO device prepares the data. CPU will be blocked until data transferred to main memory. So that preparation time depends on the IO speed, Transfer time depends on the main memory speed. Okay, accordingly we can calculate percentage of CPU time busy, percentage of CPU time blocked. Okay, right. So here whenever 8 word data available in the buffer, then it is transferred to main memory. So machine cycle given 2 milliseconds. How much percentage of CPU time is consumed? CPU time consumed means percentage of CPU time blocked in the DMA operation. Okay. So first here calculate the preparation time. Preparation time denoted as X. This preparation time depends on the IO speed. So here 1 KB data transferred in 1 second. Okay, 8 word data transmission takes how much time? From 1 kbps device, if we want to prepare 8 word data, how much time is required? Okay, so what is the word size? That is equal to 32 bit. 32 bit is nothing but a 4 bytes. This is equal to how much? 32 byte. Is it clear? Right. So this is equal to 32 byte upon 1 KB seconds. Byte cancel. So when we want to calculate the time unit, kilo considered as a decimal value. Storage के लिए kilo is binary. Time unit के लिए kilo means decimal unit. So this is 32 milliseconds. So X value equal to 32 millisecond. Then what is Y? Y means transfer time. Y means transfer time. Okay. Transfer time depends on the main memory speed. In the question, machine cycle time given. In one machine cycle, one word data will be reading or writing from the memory. Okay, machine cycle definition is number of CPU cycles required to perform memory read or memory write operation. So in one machine cycle, one word accessing will be takes place. But here we need to transfer 8 word data. Okay, so here in one machine cycle, comma, one word accessing takes place. Therefore, 8 word access, 8 word transmission takes 8 machine cycles. Okay, students? So, Y equal to 8 into machine cycle time 2 milliseconds. This is 16 milliseconds. Is it clear? Now, percentage of CPU time is blocked. Percentage of CPU time blocked. Percentage of time CPU blocked. Blocked is nothing but a hold equal to Y upon X plus Y into 100. Now substitute the values. Y value is 16 upon X value 32 plus 16 into 100. Compute this and report the value. That is 33.33. 33.33%. 33.33% of CPU time is consumed for the DMA operation. Okay, because CPU will be blocked when DMA transferring the data. How much time CPU is blocked? This much time. You know, this much percentage of time CPU will be blocked in the DMA operation. You know, remaining time CPU busy with other program. Okay, students. So this is the way of solving the DMA related questions. Okay. All right. Let me see how many of you given right answer. Subhashni given right answer. Yeah. Tulsiram given right answer. Rahul, Sobit. Okay, correct. Very good. Vandit. All right, this is a way to solve the DMA related question. Okay, students. So up to now, all the areas and all the concepts covered in the computer organization subject. Okay, students. So finally, all the best. All the best, my dear students. Okay. Exam point of view, do the hard work. Okay. Finally, hard work is matter, right? Practice all the concepts, because in the exam they may ask any question from any corner. Okay. We cannot say that only so and so topic is very important and some other topics are less important. Not like that. So every topic is important. Okay. So you please refer all the corners of the subject. Okay. Then you can easily answer all the questions. Okay, students. Thank you so much all for your wonderful support to analyze the important questions in the computer organization subject. Okay. We already completed all the questions in every area of a computer organization subject. Okay. Thank you so much all. All the best. God bless you all. Thank you. Bye bye.